The Webb glance is such a long way out that it is catching light that has already been voyaging for over 13 billion years. Yet, the universe has been expanding, and thus the light has been stretching as well. For the most distant worlds, we're looking back to just before the Big Bang. The vastness of the universe might appear infinite, but it began in its entirety from what we allude to as the singularity. Currently, it operates in this manner. One might interpret the Big Bang hypothesis. The James Webb Space Telescope, JWST, however, has revealed significant mysteries concerning the formation and growth of the universe, leaving us speechless. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to alter our understanding. The James Webb Space Telescope, named after the well-known NASA executive James E. Webb, remains a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope. The JWST came about because of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency. It surpasses the abilities of its predecessor. It utilizes cutting-edge design and technology, enhanced for concentrating on the universe in incredibly fine detail. Unlike the Hubble, the JWST conveys clear and sharp images of faraway celestial bodies. Working primarily in the infrared range, this feature permits it to penetrate astronomical dust and capture divine objects that were previously hidden from view. With its massive 6.5-meter primary mirror, made up of 18 hexagonal sections, the JWST dwarfs the Hubble's reflector in size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it revolves around the Sun in harmony with Earth, guaranteeing a steady and continuous view of the universe. While looking into the far-off parts of the universe, it not only explores light years of space, it also involves a type of time travel. The JWST uses infrared instruments to observe celestial events that date back billions of years. As a result of the expanding universe, the light emitted by these objects undergoes redshift, moving from the visible spectrum to the infrared. Luckily, JWST can detect this redshifted infrared light from heavenly bodies at extreme distances, empowering researchers to study the birth of stars, investigate galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the observable universe. This finding challenges the validity of existing concepts of cosmic formation, provoking a reassessment of our core cosmological assumptions. To better understand how we arrived at this point, we should take a short journey through the history of space exploration. Early civilizations like the Greeks and the Chinese laid the groundwork for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical foundation for space travel. Midway through the 20th century, influential astronomer Edwin Hubble made historic revelations in cosmology and observational space science. His observations revealed that far-off nebulae were actually separate galaxies, forever altering our understanding of the Milky Way and the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving away at faster rates, demonstrating the post-World War II expansion of the universe. The history of space exploration marked the beginning of the space race with the Soviet Union's launch of Sputnik in 1957, the first artificial satellite in orbit. Yuri Gagarin's 1961 spaceflight and the Apollo 11 moon landing in 1969 were significant milestones. Fast forward to 1990, when the Hubble Space Telescope was launched, providing remarkable clarity and stunning insights into the cosmos. The journey from ancient observations to the marvels of the James Webb Space Telescope highlights the constant evolution of our understanding of the universe. Hubble uncovered the boundlessness of space and changed fundamental ideas in astronomy. Take, for instance, the famous Pillars of Creation image in the Eagle Nebula, a star nursery sculpted by massive columns of gas and dust. Another major achievement was the Hubble Deep Field image, which captured thousands of galaxies in what seemed to be a void. Hubble also examined exoplanet atmospheres, identifying components like water and organic molecules on distant worlds, hinting at the possibility of habitable zones beyond our solar system. By tracking the development of the closest observed supernova, SN 1987A, Hubble shed light on the life cycle of massive stars. These accomplishments firmly established Hubble's legacy as a cornerstone of modern cosmology, dazzling the world with its incredible discoveries. Its successor, the James Webb Space Telescope, was launched to build upon these advancements and refine our understanding of the cosmos. The current prevailing theory of the universe's origins, the Big Bang hypothesis, states that around 13.8 billion years ago, the universe began as an extremely hot and dense singularity. It rapidly expanded, giving rise to matter, energy, and the fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the large-scale structures we see today. The Big Bang theory also explains phenomena such as cosmic microwave background radiation, the abundance of light elements, and the universe's large-scale structure. Despite being widely accepted, the theory faced skepticism early on. Alternative models like the steady-state theory proposed a universe without a specific beginning. Concerns arose about evidence for the initial singularity and anomalies in observed data. Most objections were eventually addressed, especially with the discovery of cosmic microwave background radiation in 1965, aligning closely with Big Bang predictions. Space missions like COBE and WMAP, along with technological advances, further supported the theory. Enter the James Webb Space Telescope. Equipped with advanced infrared instruments, JWST can peer through cosmic dust and capture the universe's earliest light. It observes objects formed shortly after the Big Bang, focusing on stellar nurseries and hidden regions where stars are born. Infrared light, with longer wavelengths than visible light, can penetrate interstellar dust, overcoming one of Hubble's main limitations. JWST can detect cooler objects like brown dwarfs, distant exoplanets, and ancient galaxies. As celestial bodies move away, their light shifts to longer wavelengths, redshift. JWST's infrared sensitivity allows it to detect these redshifted signals, capturing early light from the universe and offering valuable insights into its formation and evolution. Energetic events such as black hole mergers and new star births emit primarily infrared radiation, expanding JWST's investigative potential. This telescope can explore phenomena that would otherwise remain hidden or unnoticed. It complements optical telescopes like Hubble by providing enhanced sensitivity to infrared radiation. This capability allows JWST to delve deeper into space and unveil hidden wonders, offering a more comprehensive view of the universe. Through its advanced instruments, the James Webb Space Telescope has allowed scientists to peer further back in time than ever before, capturing light from the earliest periods of the universe's existence. These discoveries raise profound questions about our foundational models. The detection of mature-looking galaxies, only a few 100 million years after the Big Bang, implies that galaxy formation may have begun much earlier, or evolved much faster, than previously believed. This challenges the standard cosmological timeline and introduces new possibilities for how matter clustered and evolved in the infant universe. One hypothesis suggests that early stars and galaxies formed from incredibly dense pockets of dark matter, which may have accelerated their development. If proven true, this would not only adjust the timeline, but also deepen our understanding of dark matter's role in shaping the universe. JWST has also begun to identify atmospheres on distant exoplanets with far more detail than ever before. By analyzing the light passing through an exoplanet's atmosphere during a transit, scientists can detect specific molecules such as carbon dioxide, methane, and even water vapor. These chemical fingerprints are vital in the ongoing search for potentially habitable worlds, and even signs of life beyond Earth. The telescope's sensitivity allows it to probe planets within the habitable zones of distant stars, examining the chemical makeup of their skies. If biosignatures or indirect signs of life are ever detected, it would be one of the most transformative discoveries in human history. Beyond exoplanets, JWST is also revolutionizing our understanding of star birth and death. In stellar nurseries, the telescope has revealed stunning details of how gas and dust collapse to form stars, and how young stars influence their environment with radiation and winds. At the other end of the life cycle, JWST observes the dramatic remnants of supernovae and the formation of black holes. It studies how the heavy elements forged in these explosions, like carbon, oxygen, and iron, are scattered into space, eventually becoming the building blocks of planets and life. Another remarkable area of study is the interaction between galaxies. By observing merging galaxies and the massive black holes at their centers, JWST helps astronomers understand how these cosmic titans influence each other, shaping the structure and future of the galaxies they inhabit. Through all of this, JWST doesn't just provide stunning images. It delivers data that forces scientists to ask deeper questions and consider new theories. Its findings inspire not just adjustments to existing models, but entirely new frameworks for understanding space, time, and the origin of everything we know. In many ways, the James Webb Space Telescope is a time machine. Its powerful infrared vision looking not just into the cosmos, but back into the very fabric of time. As new discoveries unfold, we are reminded of how much there still is to learn, and how each revelation brings us a step closer to answering humanity's oldest questions. Where did we come from? Are we alone? And what is our place in the universe? Billions of years. These observations also contribute to more general inquiries about the fundamental nature of the universe, including its elements, structure, and the factors that control its evolution. The Hubble Space Telescope was revolutionary, but it was limited in its ability to observe the early universe. Its main restriction was its inability to penetrate cosmic dust effectively and detect infrared light emitted by ancient galaxies. Older telescopes were based on visible and ultraviolet light observations, which made it difficult to explore the beginning of the universe, as these wavelengths were absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope, JWST, is a significant advancement in observing gas and galaxies from the beginnings of the universe. As opposed to its predecessors, the JWST can observe celestial objects that came into existence within hundreds of millions of years after the Big Bang. With its sensitivity to infrared light and advanced imaging capabilities, the JWST has discovered a wealth of ancient galaxies, offering remarkable clarity. In order to comprehend the universe's evolutionary history, preliminary results from JWST observations have stirred waves in established cosmological models. The in-depth data presents a number of aspects that challenge prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand the structure and evolution of the universe. Discrepancies between observed data and theoretical predictions have sparked ferocious debates in the scientific community. Observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some early galaxies appear to be more developed and formed more quickly than anticipated, challenging conventional models predicting slower development. The discovery of unimaginably massive galaxies challenges the presumed order and distribution of cosmic structures. These findings reveal that the cosmic web is more complex and dense than initially considered. These observations provide fascinating opportunities and raise new questions for further exploration. The existence of large structures in early models challenges our understanding of cosmic structure formation, prompting researchers to refine models for a better explanation of how these massive structures quickly grew after the Big Bang, a conundrum that requires an explanation without contradicting basic cosmological principles. Significant differences in the conditions of the early universe, compared to predictions based on existing models, have also been revealed. These variations may suggest previously unknown physical processes, unanticipated circumstances, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to reconsider and enhance our models of the universe. All we can do at the moment is acknowledge that additional research is required to incorporate these surprising observations into a more comprehensive understanding. Initial observations often provide exciting glimpses into the universe, but in-depth investigations sometimes reveal differences. For example, early observations may show specific arrangements or properties within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are extremely intricate and require meticulous investigation in order for us to comprehend their true nature accurately. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is one illustration. By analyzing the light emitted or absorbed by astronomical objects, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of these bodies to the cosmic tapestry. The JWST has uncovered numerous cases where the initial observations were misleading. For instance, early observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST revealed fascinating differences. Evidence of heavier elements or compounds previously misidentified or misunderstood. This challenges conventional ideas about the early universe's chemical composition and the mechanisms accountable for the growth and dispersal of galaxies over vast distances. First hypotheses regarding galaxies in the earliest universe were founded on preliminary observations, suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions. The James Webb Space Telescope continues to redefine our understanding of the universe by shedding light on previously hidden corners. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures, such as the presence of carbon dioxide, water vapor, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that could support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe star formation in areas where young stars are surrounded by dense clouds of gas and dust, regions that optical telescopes cannot penetrate. With its capacity to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the steps that lead to the formation of stars and planetary systems. By studying these processes, astronomers are discovering a deeper understanding of how stars like our Sun come into existence and evolve over time. An additional remarkable feature of the JWST is its ability to peer into the interiors of galaxies and observe black holes, particularly supermassive ones believed to reside at the centers of most large galaxies. Scientists use JWST instruments to observe the behavior of matter around these black holes, providing new insight into their growth, their influence on galactic evolution, and the powerful jets of energy they produce. These findings are helping astronomers piece together how galaxies and their cores came to be and how black holes evolve, each influencing the other's growth. Moreover, the JWST's discoveries are not only answering long-standing questions, but also raising new ones. As it probes deeper into the history of the universe, it is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current models of the cosmos and open up new research avenues that were previously unimaginable. The discoveries of the JWST are not just pushing the boundaries of our understanding. They're helping to reshape the fundamental principles of how we view the universe itself. As the JWST continues its mission, it is not only enhancing our understanding of cosmic origins, but also revolutionizing how we approach the study of time and space. Its unprecedented precision in capturing faint light from the earliest periods of the universe allows scientists to effectively look back in time, witnessing events that occurred billions of years ago. This capability is crucial for piecing together the timeline of cosmic evolution, from the formation of the first stars and galaxies to the large-scale structures we observe today. One particularly groundbreaking aspect of JWST's work is its ability to detect and analyze the atmospheres of exoplanets in distant solar systems. By studying how starlight filters through these atmospheres during planetary transits, researchers can identify the presence of water vapor, carbon-based molecules, and other potential biosignatures. These findings hold profound implications for the ongoing search for extraterrestrial life, suggesting that habitable environments might be more common in the universe than previously believed. In parallel, the JWST is providing vital data on the life cycle of stars. It captures the birth of stars and stellar nurseries, dense, dusty regions where protostars ignite from collapsing gas clouds. By tracing the development of stars at various stages, astronomers are gaining a clearer understanding of the processes that govern stellar evolution and the formation of planetary systems. This information not only sheds light on our own solar system's history, but also allows comparisons with others, potentially uncovering unique conditions or patterns that foster life. The telescope also contributes significantly to our knowledge of dark matter and dark energy, two of the most mysterious components of the universe. By observing how light from distant galaxies is bent by gravity, a phenomenon known as gravitational lensing, JWST helps map the distribution of dark matter. Meanwhile, its detailed measurements of the expansion rate of the universe offer new clues about the nature of dark energy, challenging existing theories and inspiring new models that better fit the data. Additionally, the JWST has proven instrumental in revisiting and reinterpreting past discoveries. Many celestial bodies previously observed by Hubble or ground-based telescopes are now being studied with greater clarity and detail. In many cases, this has led to surprising revisions in our understanding, revealing previously unseen structures, motions, or interactions. Perhaps one of the most transformative impacts of the JWST is its ability to inspire. Beyond its scientific contributions, it stands as a testament to human curiosity, collaboration, and ingenuity. Built through the efforts of thousands of scientists, engineers, and researchers across the globe, it represents a shared pursuit of knowledge that transcends borders and generations. As data continues to stream in, the scientific community eagerly anticipates new revelations. Each image, spectrum, and measurement not only answers long-standing questions but often raises new ones, pushing the boundaries of what we thought was possible. The JWST is not just observing the universe. It is reshaping how we understand it, how we explore it, and ultimately, how we see our place within it.